In this lecture, I shall be talking about basically covariances and some of their properties, but then before that, in order to introduce covariances, I will start with some of the basics of statistics. Okay. Suppose x is a random variable taking values, let us just say x1 to x1, x2, x3 etcetera, infinitely many, with probabilities p1, p2, p3 etcetera, where naturally 0 is less than or equal to pi, strictly less than 1, and summation pi I is equal to 1 to infinity is equal to 1. Then the mean of random variable, mean of x, which is denoted by expected value of x, and this is equal to summation I is equal to 1 to infinity x I multiplied by p I. This I suppose all of you know it. Okay. Then the variance of x, which is expected value of this is equal to, so basically summation I is equal to 1 to infinity p I into x I minus here. Please look at it, you should write here a value of x, a value of x is x I minus the mean, the whole square, expectation means this one multiplied by the corresponding probability. So, this one multiplied by the corresponding probability p I is equal to 1 to infinity. This is for discrete random variables, but for continuous random variables, here x is a random variable with probability density function, say f, then mean of x, which is same as expected value of x, which is equal to integral x f x dx, integration over suppose x is a positive random variable, that means for minus infinity to 0 the density is anyway 0, from 0 to infinity it is going to be positive. Okay. So, even if it is a positive random variable or even if it is not taking some values in this interval minus infinity plus infinity, one can always write minus infinity plus infinity, because the place where the random variable is not taking the values, the corresponding density will be anyway 0. So, I can always write minus infinity plus infinity. Then again the variance of x is equal to, the formula is the same thing, this is equal to integral x minus okay. Now, there are some nice properties. What are the properties? First, this is whether you have a discrete random variable or you have a continuous random variable, the properties that I am going to write, they are always true. What are the properties? Let me write down properties like this: expected value of a x plus b is equal to this means we have a new random variable y, which I am defining as a times the random variable x plus b, where a and b are constants. So, the mean of this random variable is a times the mean of the old random variable x plus b. Okay. Now, 2 variance of a x plus b is equal to a square variance of x. Variance of a x plus b is equal to a square, that means the b does not have any impact. Whatever b you take, it does not matter, it will be a square variance of x. Okay. Now let us have this covariance. So, for covariance you need to have two random variables x and y, okay, and you also need to have a joint probability density function. So, there are two random variables x and y are two random variables, and you have the joint probability density function f x y. Then the covariance of x y is equal to basically expected value of this is equal to let me explain. Note that these small x's and small y's, these are the values taken by the variable, and the variables are represented by the capital letters capital X and capital Y, and this thing expectation of x, it is a constant value, expectation of y, this is a constant value. So, covariance of x y is expected value of x minus expectation of x into y minus expectation of y. So, this is like this, the product of x minus expectation of x into y minus expectation of y, and you should write the density function because expectation you are taking, and with respect to x and with respect to y dx dy, and this is over the whole thing. And you can have similar definition for discrete random variables also, which I am not writing. Now, well, what will be covariance of x with x? This will be right, and this will be, which is nothing but variance of x. This is nothing but variance of x. And there are some more formulas. What are the formulas? Say covariance of let us just say x plus y with z is nothing but covariance of x z plus covariance of y z. Is this true? Why? Just apply this one. Expected value of x plus y minus so x plus y minus expectation of x plus y is expectation of x plus expectation of y. So, minus is this and multiplied by z minus expectation of z. So, this is nothing but expectation of, you see, x minus expectation of x into z minus expectation of z, then y minus expectation of y into z minus expectation of z. So, x with z and y with z, expectation of plus expectation of yes. So, covariance of x plus y with z is equal to covariance of x z plus covariance of y z. So, covariance of x with a constant, what is that? Covariance of x with a constant is 0. Again you apply the formula, x minus expectation of x, constant is a, the mean is also a minus a is equal to 0. So, multiplication of that thing is 0. So, you are going to get 0. So, covariance of x with a is 0 and covariance of a x plus b with c y plus d, this will be first before that covariance of a x with y is equal to a times covariance x with y. Again you apply the formula, a x means a x minus a into expectation of x. So, a is going to come out. So, x minus expectation of x into y minus y expectation of y. So, covariance and a has come out. So, a times covariance x y and covariance of a x plus b with c y plus d is equal to a c covariance x y. A times c covariance x y. Okay. Now, suppose we have 3 variables. Let us just say we have 3 variables x 1, x 2, x 3, okay. And suppose x 2 is equal to 2 x 1 minus 1, x 2 is equal to 2 x 1 minus 1. Okay. Now, what is now this matrix? Let us just see covariance x 1 x 1, covariance x 1 x 2, covariance x 1 x 3. covariance x2 x1, covariance x2 x2, covariance x2 x3, covariance covariance x1 x1 is variance x1, covariance of x1 with x2, x2 is 2 x1 minus 1. So, this will be 2 times variance x1. x1 with x1 is variance x1, x1 with x2, x2 is 2 x1 minus 1. So, this with x1. So, 1 times 2, this is 2 times variance x1, and covariance x1 x3, let me just write it like this, whatever it is there. Okay. Now, covariance of x2 with x1, that is 2 times, right, and x2 with x2, this is 4 variance x1, and x2 with x3, x2 is 2 x1 minus 1, this will be 2 covariance and anyway there is a third row. Now, what can you say about the first 2 rows? Dependent. So, what will happen to the determinant? 0. The determinant value will be 0. So, because of just this relationship, what is happening, whatever may be your covariance matrix, if 2 variables are linearly related, the rank of the matrix is going to be decreased and it will not have full rank. It will not have full rank, that you can very clearly see, and the determinant will become 0. Okay, and the determinant will become 0. And I am not writing these things. This will be covariance x1 x3, and what will be this? This is 2 times, this will be variance x3. Okay. It is not really important, I am only interested in the first 2 rows. I am only interested in the first 2 rows. So, if 2 variables have linear relationship, it is going to affect the whole of the covariance matrix. Have you understood it now? It is going to affect the whole of the covariance matrix. So, that as you can see the rank here, these 2 are linearly dependent rows. These 2 are linearly dependent rows. So, that the determinant is going to become 0. So, you are forced to reduce, you are forced to do feature selection in this case to make the determinant non-zero. Have you understood what I wanted to say? if you get a matrix covariance matrix with determinant as 0, okay, somehow you should find out which one is doing it or which one is making it. So, that that particular linear combination or whatever it is, somehow you want to remove it, so that you will make it the determinant non-zero. Somehow you have to find the largest minor for which the determinant is non-zero, largest minor you need to find out. I hope you are understanding the terminology that I am using. You understand the word minor? You are supposed to find the largest minor, and that will actually tell you the number of independent variables, or it will actually tell you how much rank at most you can make it. So, you should remove the rest of the things, somehow you should find them to be, you should find those things and you should just remove them, because those variables are going to act as noise. Any question, please?
Given this covariance matrix, we can say which two variable are related feature, which two features are related?
Look at this one, this variance x 3, this is somehow not taking any part here. So, somehow x 3 you should take it out. You see, you look at this 2 by 2 matrix, this row you multiply by 2, you are going to get this. Look at this with this, again this row you just multiply it by 2, you will get it. Look at this with this row you multiply by 2, you are going to get this. This sort of thing you will not get if you are looking at this 4 variance x 1, 2 covariance x 1 x 3, 2 covariance x 1 x 3. So, you are supposed to get just variance, I mean covariance, I mean this one you have non-zero determinant, probably this also has non-zero determinant. Are you understanding? This non-zero determinant, this also non-zero determinant, but you have here 0 determinant, because this is this row, if you multiply it by 2, you are going to get this. So, since these two rows are dependent, so here some variable should be removed. On the other hand, this is non-zero determinant, this is also non-zero determinant. So, here you should keep one variable, and from here you should remove one variable. So, naturally the variable that you are going to keep is x 3, and the variable that you will be removing is something from here.
Sir, one more question, sir. If two features are non-linearly related to each other, can we use same
non-linearly related?
Yeah, can we use same concept?
No. See, all these things, they are linear.
This is only for linear.
Have I written anything for non-linear? If it is non-linear, have I made any statement about what may be happening? No. So, about non-linear relationship, I do not want to make any statement on this. We are only looking at linear case, the dependency or independency, they are also linearly independent or linearly dependent. Okay. These vectors are said to be linearly independent, that is the definition that we read. Similarly, they are said to be linearly dependent if they are not linearly independent. So, I am not looking at the non-linear part of it, and if it is non-linear, how to go about doing it, at least I mean I cannot make any statement using these things. That is a real serious problem which people are really aware of it, but they are not been able to find solutions acceptable to everyone. Okay. They have not been able to find solutions acceptable to everyone. I am only talking about linear case. Yeah. Now, any doubt? I can say that you find the largest minor or that largest square matrix with non-zero determinant. Saying it is easy, but then you have to look at all those combinations which may be difficult. Okay. But then the principle I hope you have understood it. If your variance covariance matrix has the value determinant as 0, determinant value as 0, somehow you should find out those variables which are causing this 0 and you should remove them. Okay. But how are you going to do it, that I think the principles are clear to you, but then you should act how are you going to implement it, which are I mean you would like to implement it in such a way that it is feasible to implement it. I mean you do not want to do an exhaustive search, then which will make your life miserable. That I think one should try to find out some methods for this, and it is not really I mean there are some things I think they are already existing in the literature. The moment you have your covariance matrix has determinant 0, okay, there are some papers which you can find in the literature about how to go about removing those features, so that you would like to make it non-zero. So, this one I think I will stop here.